All right, any questions before we get going? All right, hearing none, let's go ahead and get started. So today we're going to cover section 3.4. We're looking at graphs of polynomial functions. So as we've seen before, polynomial functions are smooth graphs with no sharp corners or breaks, and the domain basically is the whole set of real numbers. Now when we're looking at polynomial functions, usually we factor it into the factors. And what happens is sometimes we're going to have a multiplicity, which is the number of times a factor appears. Sometimes we might have, say, an x plus 1 to the third, or might have x minus 2 squared. So we're going to have multiplicities, and it's basically the number of times it appears in that function. And we're going to use that eventually to help us determine how to draw the graph from just an equation. And we're also using the factoring and the zero product rule to find our x-intercepts of the polynomial function. So what we're going to do now is we're just going to look at a few polynomial functions and kind of look at the intercepts and look at multiplicity. And then from there, we're going to kind of look at some graphs and try to figure out things from there. And then we'll move into actually drawing graphs as we go. So the first thing we're going to look at is we need to find the x or t. Some of these are in terms of t, some of them are in terms of x, intercepts, and the multiplicity. Well, since this one's factored already, all we have to do is set each of the factors equal to 0 and solve for the variable. So in this case, the variable is t. So first one, we end up with t equals 0. For t equals 0, divide by 4, we get 0. And how many times does that occur? Well, t is to the first power, so the multiplicity is equal to 1. Now here, if we set this equal to 0, t minus 2 equals 0, that gives us t equals 2, and the multiplicity is equal to 2 because we have that power of 2. Now here, the last one, when we set that equal to 0, we get t equals a minus 1, and we're back to multiplicity of just the 1. And so this is, again, factored form, so we don't really have to do too much. Not always are they going to give it to you in factored form. Sometimes you're actually going to have to factor it. And so, but when we do have it in factored form, we get our zeros or x-intercepts really easy, and we can also get our multiplicity really easy. Now this is one where we actually have to do a little bit of work, not a lot in this case, but we still have to factor. And so the first thing we can do is when we can factor out an x. That's common to everything. And so that gives us x squared plus 6x minus 7. Now we have to decide, can we factor this? Well, I'm just going to go and try, and I'll put my x's because that breaks down into x and x. One's going to be plus, one's going to be minus to get the negative here. And so then after that, I have to decide, okay, how do I get a plus 6 in middle? Well, if I use a plus 7 and a minus 1, I'll have a 7x minus x, which is going to give me a 6x, and then that gives me minus 7. So that's going to be my factored form of this polynomial. So now I can set each of the terms equal to 0. And when I do that, I'll get my x-intercepts, and then I also will get the multiplicity. Well, the multiplicity in all of them is just 1 because they all just have that 1 up here. We don't have anything else. We just have a 1. And so on all cases, the multiplicity is equal to 1 in all cases. And so then my zeros are going to be, well, if I set the first one equal to 0, I get x equals 0. If I set this equal to 0, I get x equals a negative 7. And if I set the last one equal to 0, I get the x equals a positive 1. Now, in all these cases, these are the zeros, but if they actually want you to write the intercept, we can do that. That's pretty easy. We just, plug in x value and then 0 for the y. So then, that would be negative 7, 0. And this would be 1, 0. So if they want us to put it into the XY form, we can do that. Or if they just wanted us to solve for X, we can do that. So again, it all depends on how the question is asking for it to be input into the MOM. Or when I do it on the test, I'll hopefully be a little more specific sometimes than MOM is. All right, so the next one here we see we have x, we've got this, and we've got this. So we've got two long trinomials and then x. So the key is, can we actually factor anything? Well, if we look at this, the way this is set up, this is going to be a perfect square trinomial kind of thing, because if we take and do this one and break it apart, 2x and 2x and minus 3 and minus 3, that will give me 4x squared minus 6x minus 6 more x, which is the minus 12x, then plus 9. So that factors into those two. And this one also factors into perfect square trinomial. This one's going to be x plus 4 and x plus 4 because this is half of that. Okay. So if we square that, that's 16. That's 4x plus 4x is 8x. And so now this is written as x times 2x minus 3, the quantity squared, times x plus 4, the quantity squared. So now we have x equals 0, or if we want, the 0, 0, that has multiplicity, and that's equal to 1. We can set this middle one equal to 0, and so we get x equals 3 halves. So if we do that, that's going to be 3 halves 0, but its multiplicity is 2. And this one, if we set equal to 0, we get x equals a negative 4, or that's going to be a negative 4, 0. And its multiplicity, again, is also 2 because we have the power of 2. Okay. So these are how we can look at different kinds of polynomial functions, and we can determine what their zeros are, the x-intercepts, as well as the multiplicity. And again, this multiplicity is going to come into play when we're actually graphing these or determining what's a graph, what its multiplicity is. Okay. So moving on to that, the graphical behavior of polynomials at the intercepts, so these things we just found, the x equals 0, 3 halves, and negative 4, the multiplicity of those determine the behavior of the graph at those intercepts. So if we have zeros with odd multiplicity, like 1, 3, 5, 7, and so on, basically your graph's going to cross or intersect the y-axis at that intercept. So whatever the intercept is, it's going to cross or intersect it there. And if we have an even multiplicity, basically your graph is just going to touch it or it's tangent to. So if we look at our graph down here, we can see, it crosses at a point like this, and it touches or is tangent at those points there. So that's kind of what we're looking at when it crosses at that intercept. So that's, the intercept there, that's the intercept there, and that's the intercept there. So that's what we're talking about when we're either crossing or we're just touching or tangent. Now, to be a little more specific, if we're given the graph of a polynomial function and we know the degree of it, so it's some n, so this is kind of the example here. If this has a degree of n for this graph down here, we can identify the zeros from the graph, and we can also determine what the multiplicity is. Now, when I said up here, odd multiplicity crosses and intersects, there's a specific one. If we have a multiplicity of 1, basically it's going to appear like it's a line going through that 0. So in that case, none of these are like a line. But if we had something like, something like that, that's basically a line going through the 0, and this would be like some kind of a negative x to some second power function. And so those are kind of what we're seeing here. That would be a multiplicity of 1, where it just is like a straight line. Now, if it's going through the 0, multiplicity is going to be odd. So this one here, it goes through the 0, it's odd. So we don't know if it's a 3 or a 5 or a 7 or something like that, but we know it's going to be something odd. And then if it touches or bounces off at the 0, basically your multiplicity is even. So things like this, where it goes down, touches it, and comes back up, and come down again and touches it, those are going to be even multiplicities. So what we're going to do is, from this graph, we want to find the different zeros, and then we want to find their multiplicities. So if we look at the first one here, that's crossing at x equals a negative 5. So we have x equals a negative 5. That's the 0. Now, if they want it, we can say also that's a negative 5 comma 0 if they want the actual intercept point. We can do that. And we know it's going to be an odd function because it's crossing. And so we know that it's odd. And now before we go any further, I'm just going to keep it at odd. And then because what we have to do is we're going to have to add up to a total of 9. So let's find the other 2. So this one crosses at x equals -1. And so that's a -1, 0. Now it touches and then just bounces right back up. And so that's going to be an even function based on, this number 2 part. It goes down and touches and then goes back up. And so that's even. And then this last one is going to be at x equals 3. So then we can say x equals 3. And so we have 3, 0, and we know that's even. All right, so if we say that this one here is odd, we know it's not a 1 because a 1 would be more of a straight line. Let's call that one n equals 3. So that's our multiplicity, okay? So that's the multiplicity. And then we go to the next one. Okay, well, the next one, it looks like a normal, x squared function. It just has a straight down and up. So that one probably is 2. Now the next one's even 2, but if you notice, it's pretty broad here at the bottom. So it's going to be bigger than 2 because if that one's 2, this one's probably 4, maybe 6. And so far we have 5. Possibility is 9. So this one then has to be 4 for the multiplicity because 4 plus 2 plus 3, that gives us a 9. And if you add all the multiplicities together, that's going to give you the degree of the polynomial. So that sometimes helps us determine, if we have an equation where we know how many degrees it is. It's a 5th degree, 9th degree, or whatever. And so we can draw the graph, and then we're going to draw the graph based on, the zeros and what the multiplicity is at each of those. And so it's, drawing by hand, it's going to be hard. It's going to be a lot easier if you type it in your calculator, of course. But what we're going to do is we're going to try to draw most of these by hand as we go, and then we can check them with a calculator if we want to. Okay, so the sum of all the multiplicities is going to be n, and so if we take, and I just called it n here, but it's not really, each one of those isn't really n, that's what I put it as just to make it so we knew it was something, but that's the multiplicities. And so all those added together is going to give us the total of 9. All right, so let's look at the next one. So now if we're given a polynomial function, so instead of being given the graph, if we're given a function, they want us to sketch the graph. So what we have to do in order, we find the intercepts, both x and y. Then we check for symmetry. If it's an even function, it's symmetrical about the y-axis. If it's odd, and so on. But really, that one, if that's going to help us, if we know, remember our n behaviors, that's going to be even, and k is greater than 0. This one is even, and k is less than 0. And this one's going to be odd, and k is going to be greater than 0. And this one's going to be odd, and k is less than 0. So that's really going to be the key things we need to know for n behavior. Then we're going to use multiplicities of 0 to determine the behavior at the actual intercepts. So wherever it crosses those intercepts at. And so we'll know, does it go up and touch at that point, or does it cross more in a linear fashion, or does it kind of have more of the odd function kind of looking? So that's going to help us use the multiplicities, determine, which one of those kind of features we're going to have. Determining in behavior, that's what this is, but also comes in with the symmetry thing. Then we're going to use the behavior, the behavior at the intercepts, and we'll actually sketch the graph. And the key thing to remember is number of turning points is going to be n-1 as the max. So if we turn too many times, that's not going to work. So we have to make sure n-1 is the max number of turning points. And then after we sketch it, then we can kind of check with technology, your calculator, to see, does that really make sense on what we have? All right, so what do we have for here? Well, we've got 2 factors, or basically 2 intercepts. We've got x equals a -3, and the multiplicity is going to be equal to 2 because we have that 2 value. And then this one is x equals 2, and its multiplicity is equal to 1. Okay, so our degree of the polynomial is equal to 3 because we have 2 here plus 1 here, so that's going to be a degree of 3. So it's going to be some kind of an odd function. There's a 1 here, there's a 1 here, so when we multiply it out, k is greater than 1. So, our end behavior is going to look like this. In between, that's what we have to do with the x equals minus 3 multiplicity 2 and x equals 2 at multiplicity 1. So what I'm going to do is I'm going to kind of draw axes here. All right, so we know x equals minus 3, and I'm not going to put specifics, exactly where it is because it's going to be kind of just a rough graph. So that's going to be at minus 3. We also have something at 2. And so now what we need to do is at minus 3, the multiplicity of 2. So it's just going to come and touch that. It's not going to cross the point at that point. And at x equals 2, the multiplicity is 1. So it's going to be kind of like almost a straight line going through that point there. So what we need to do is remember it's degree 3. So we're going to have it coming up over here somewhere, and it's going to be coming down over here somewhere. Okay, so now we just have to draw what's in between there. Now, one other thing we should get before we go on is what is our y-intercept, because we need to know, does it hit, here, down here, up here, or something like that. So if we get our y-intercept and we plug in 0 for x, if you put 0 here, that's going to be 3. 3 squared is 9. And then times, and you put 0 here, that's a minus 2. So times 9 times a minus 2, that's equal to a minus 18. So our y-intercept is 0 minus 18. So it's going to be somewhere down here. So that's a negative 18. Okay. So drawing our graph now, we know it starts down here. When it gets to 3, it's just going to touch and bounce back down because we have that multiplicity of 2. So it's going to come up. Well, let me get the eraser here. And we know it's going to go up there, so we just have to draw what's in between now. Let's see if I can get this to work now. So it's going to come up here. I'm going to touch there, come back down. We're going to have it touch through that white. I was going to erase that now. Come down through our axes here. Then it's going to come back through the 2 and it go back up. So the end behavior is like this. It comes up and just touches the axis there, goes through the negative 18, then it comes up back through the 2. So this is going to be what we should get if we plug that into our calculator. So let's test that. And if we go over to our calculator, now what we have to do is we have to type that whole thing in again. So we have our y equals. Now let's plug in what we have. So we have x plus 3 squared times x minus 2. And so then we should get a graph from that. And that's kind of what it looks like. Now see, here I didn't know exactly what it was like here. I thought maybe that was where it was because we didn't have the thing. But the general form goes up here at the negative 3, it touches, then comes back down, cuts through the negative 18, then comes back up through that 2, and then it continues on up through that. So that's, again, as far as we can get, this point here, we're not exactly sure. We could have came up with what is the minimum value there, but we didn't. We just kind of came down and said that's what it was. And so doing it in a rough graph, that's what we ended up with for ours. And again, what would have happened better is if we would have come down here a little bit further and then gone up. Okay. All right, so let's do another one. All right, so here we have, again, 3 terms this time. Now we have x equals 0. We have that as multiplicity is equal to 1. We have x equals 1, multiplicity equals 1. And we have x equals a negative 3, and our multiplicity equals 1 again. So what do we know? It's a 1, 2, 3, so it's an odd function. And here, k is less than 0. So what do we know about something with k less than 0 and odd? is going to do something like this. And so it's going to go up here to the left on the x going to negative infinity, and it's going to go down here to negative infinity when x goes to positive infinity. And then we just have to figure out how it's going to cross on all these pieces here. All right, so let's go ahead and start drawing. All right, so we have, let's get our 0 for y-intercept. So if that's 0, that whole thing is 0. So we have 0, 0. That's going to be our y-intercept, as well as it's that point right there. So we kind of have something that looks like that. And so now let's start with -3. So that's going to be somewhere over here. Then we have a +1, so let's say that's there. We'll put 1 up there, I don't know why. And then of course there's 0, 0. And so we know it's going to start up here in the corner going up, and all multiplicity is 1, so it's going to kind of be just straight lines coming down and going through. So we know it's going to come down, and that's supposed to go through that point. Then it's going to come back up, and we know it's going to go up through 0, 0. And then it's going to come back down through that 1, 0, and it's going to look something like that. Again, how high it goes up here, it's kind of hard to say, and how low it goes down here without actually plotting some points to get where that is. But this is the general shape of our graph, and that's really what we're trying to get at this point in time. And if we plot that on our calculator, what do we get? Let's see. So we're going to clear that. Let's say we have -2x times x minus 1, and then we have x plus 3, and our graph, and same spot, so it's good. So, you know, it comes down here. Again, we're not exactly sure where we're at here. Comes up here, just goes a little bit above, comes back down to 1, then it goes down here. So it follows our odd function with k less than 0, which is what we wanted. We knew it came down kind of a straight line here, straight line here, straight line here, and we'll hit the intercepts. So again, we're doing good as far as how we are graphing those and getting that in. Are there any questions on that before we move on? All right, so now what we're going to do is we're going to be given a graph, and we actually have to write the equation for it. And how we're going to do that is we're going to have to figure out some non-x-intercept point. So most likely I'm going to use a y-intercept because that's going to be pretty easy, or if there's a turning point that I can exactly tell. But usually it's going to be some y-intercept that's not an x-intercept, because of that last one we had the intercept was at 0, 0. We wouldn't want to use that one. We'd have to use something else, and so we'd have to kind of choose a point somewhere else to do that. But what we're going to do is we're going to plug that non-intercept point in after we kind of write the general form of the equation. So it's going to be something f of x equals, and now a is going to be our stretch factor. That's going to be what, you know, number comes out in front, the -2 in this case. And then it's going to be times x minus whatever our first point is, raised to whatever power we think it is. You know, if it touches, it's going to be at least to the 2 power, if not higher. If it goes straight through, it's going to be to the 1 power. If it kind of comes through at an odd angle, you know, like the power of odd 3, then we'll have a 3. If it's flattened out, then we'll have to kind of guess, is it a 5, or maybe if it's, you know, an even one, maybe it's a 4 or 6 or something like that. And so those are going to be the things we plug in. And so we'll get everything but a, and then that non-intercept point we're going to plug in and say whatever that was, we're going to plug in f of x, that was going to be our y, and whatever the x is we plug in, and then we solve it back for the a, and then our equation we can write back out as f of x equals whatever that a value was as a number times the x minus whatever to the power times x minus whatever to the power, and so on. And so that's how we're going to do it. And so let's kind of look and see what we have here. So what do we have? We've got a point here. It's going to be -2, 0. That's going to be one intercept. Now its multiplicity looks like 1 because it's going straight through. Then we have something right here, which is 1, 0, and its multiplicity is also 1. And then we have something over here, which is 3, 0, and its multiplicity is also 1. And so then I'm going to have the y-intercept here, which is 0, 3. And that's going to be my point I use, my non-intercept point. So that's going to be my y-intercept. Okay. And so from all of this, I can write something in the form of a general function. And so I'm going to have f of x equals a times. Now I have to say, okay, well, x minus 2, so it's going to be x plus 2. Now we said multiplicity is 1, so it's just to the power 1, so we don't have anything to worry about there, times. Now we have x, now this is going to be minus 1, and it's again power 1. And then we have times, and then we have x minus 3, again to the power 1. So that's my general formula. And again, what I want to do is I need to solve for a first. And so I'm going to plug in the 0, 3. So 3 equals a times, now if I just have 0, that's going to be just a 2 times a negative 1 times a negative 3. So negative 1 times negative 3 is going to be positive 3 times 2 is 6. So I have 3 equals 6a divided by 6. So a is equal to 1/2. And so I'm saying my function is going to be equal to 1/2 x plus 2, x minus 1, x minus 3, and that's going to be my polynomial of least degree. Now, it might be higher degree. They might say, oh, well, it really should be each of these, something higher. But this is the one of the least degree because based on my view of this, that should be a 1, that should be a 1, and that should be 1. And so that's going to be how I determine if that's the least degree because, I don't have any odd weird function coming down. It looks like that going through any of these. So I'm not saying that's a 3. And so that's where I have to stop at this point. And so that's going to be my function based on what I've seen. Okay, so any questions on that one? All right, so let's go to the next one. All right, so here we have, it looks like 1, 2, 3, 4 intercepts. All of them appear to go straight through. There's no curves or anything. And so they're all going to be multiplicity of 1. So I'm going to say all intercepts multiplicity equals 1. And so my intercepts are going to be a negative 3, 0. Then I have a negative 2, 0. Then over here I have a 3, 0. And then I have, it looks like a 4, 0. Okay. Now it looks like it's going through that point there, and that's going to be a 0, negative 3. Now it's not going to be where that point is right there, but it's actually touching going through that point. So that's going to be my y-intercept, and so that's going to be my non-x-intercept point that I'm going to plug into my equation once I solve for this. All right, so when I do this, now I have to plug in all of those things and then solve for a. So f of x equals a times, now if I plug that in, that's going to be x plus 3, then x plus 2, then this one's going to be x minus 3, then x minus 4. And then plugging this in, minus 3 equals a times now 0, so that's going to be a 3 times 2 times a minus 3 times a minus 4. So that's going to be a 12, and that's going to be a 6. So that's going to be 72. So minus 3 equals 72a divided by 72. So it looks like a is equal to a negative 1 over 24. Okay. So then I plug that into this, and then my function is f of x equals negative 1 over 24 times, and then I have x plus 3, x plus 2, x minus 3, x minus 4. And that would be then my function and lowest degree that I know of, and for this curvature here. Now, does it make sense? Well, yeah, because if we look at this, we have a 1, 2, 3, 4. It's even degree, which is what this shows because we have going down like this. And so that would be an even degree. And it's going down, and so I know that k is less than 0. Well, after I solve for that, I have my k is less than 0. And so everything fits as far as how it matches to the graph. We have, everything going down, so it's an even degree, which is what we have. We have four terms. We have a k less than 0, so that's what I would say would be the equation for this graph. Any questions on that one? All right, some other things we can use doing this is, one is the intermediate value theorem. So if f is a polynomial function, then if f of a and f of b have opposite signs, then there exists one value c in between a and b for which f of c is 0. So basically what happens is, if we're looking at a graph and maybe it's going something like this, and we say that we're looking at some point over here, and that's A, and we're looking at some point over here, that's B. When we do that, this point here is where A is, and that's going to give me a negative. And if I go over here, at this point, that's going to give me a positive for the Y. And there's some point between there that crosses the x-axis, which happens to be that point there, and that's going to be my C. And so this is kind of to tell us basically on some interval between A and B, if we get opposite signs for numbers we plug in on the edges or in between there, that's going to be telling us there's going to be a C in there that's going to give us an x-intercept of 0. And so basically all we need to do is plug in endpoints for the first try and see if they give us opposite signs for what f of a and f of b are at those x values. So on this case, what I would do basically is I would say, well, what is f of -1 and what is f of 1? And then I would just solve, and if those have opposite signs, then we have confirmed there's at least one 0 within that interval. And we don't have to graph it, we don't have to do anything. We just have to say, yeah, there is one there. It doesn't ask what it is. It doesn't say, graph this and show it or anything. It just says confirm there is one using this theorem. So if I plug in a -1 here, I have a -2 times -1 cubed minus a -1. So this gives me a -1 to the third is -1 times -2. So I have -2 times -1, and then minus a -1, so that's +1. So negative times a negative is positive, so 2 plus 1, so that's 3. So that's positive. So if this one comes out to be negative, then we've confirmed there's at least one 0 in that interval. So plugging in the 1, we have a -2 times 1 cubed minus 1. Well, this is going to be a -2 times 1 minus 1. So it's a -2 minus 1. That's a -3. Those are opposite signs. So there is a C between them for which f of c is equal to 0. Again, it doesn't say find the c, it just says confirm that there will be one, okay? And so that's how we're going to confirm there's going to be a 0 between there. And it could be 1.1, it could be, it could be 0, which is really what it is. If you plug in 0 here, that gives us 0, so that's where it's going to cross. But this, we know that it's going to be between the -1 and the +1. All right, so I'll do another one of those later in the extra example video and kind of show you how that works. But it's basically just plug in numbers are the opposite signs. If so, then you have that 0 between it. All right, so the next thing is going to help us eventually when we do application problems, and that's looking at the global maximum and global minimum. these are going to be the highest or lowest points of the function respectively. So, and this is only going to work for even degree. So that's kind of the key for the global min and max. It has to be only for even degree, because if you think about it, if we have an odd degree, we have something that goes like that. Well, that's just going to continue going up forever, and that's going to continue going down forever. And whatever happens in here doesn't matter, because this will always be higher than what's in here, and this is always going to be lower than whatever's in here. And so this doesn't work for odd degrees, but it does because on even degrees, no matter what we do, there's always going to be something here that could be the max, or there's something in this one where it could be a minimum, okay? And so what it is basically at some point A, there's going to be f of A that's going to be greater than f of x for all x for the global maximum. And this is actually supposed to be an A. I don't know how it became x. And it's going to be less than or equal to f of x for all x on the global minimum. And again, that's because, we're looking at it and there's going to be some value where this point here is going to be greater than all other x's here. So that f of A is going to be greater than all those other values if we plug in x. And this is going to be a global minimum, because whatever that A is, whatever we plug in is going to give us something that's going to be smaller than any of the other values we plug in for x, okay? And we can kind of see that on our graphs here. This would be like a global maximum. And over here, this would be a global minimum. So no matter how many ups and downs we have here, there's going to be one that's going to be the very lowest one, and that's going to be your global minimum. Or in this case, the very highest one will be your global maximum. Now we can have local minimum and maximum, and that can be for odd or even. It doesn't matter which one. And basically it's going to be the highest or lowest point over a certain interval and around the x equals a. So, whatever region it tells us, it can be a minimum or a maximum depending on how the graph is drawn. I went ahead and just drew it for even functions, because then you could compare it to the global minimum, and this is going to be a local minimum, because between x is equal to 2 and x is equal to 4, that's the local minimum. Or in this case here, this one is between maybe 1 and 3, and that's at a 2. That is going to be a local maximum. It's not the global maximum, it's a local maximum. And the same thing would work if we had, something like this, this one over this interval, that would be the local maximum, but if we were at this interval, that would be a local maximum. So if you have several points, you can have different local maximum depending on what your interval that it's around, okay? And again, f of A is going to be greater than all f of x on that interval for that maximum, and f of A is going to be less than or equal to f of x for all x on that interval, again, around A for your local minimum. So basically, if you look at your graph, that's going to be how you tell where the local minimum and local maximum are. Now, we're going to use those to help us solve application problems, okay? Now, this one says a rectangle has a length of 10 centimeters and a width of 8 centimeters. And what we're going to do is we're going to cut out squares of 2x by 2x on each corner. And then the sides are going to be folded up to create an open box. And we want to express the volume of the box as a polynomial function in terms of x. So that's the first thing. And then we want to find the size of squares that should be cut out to maximize that volume enclosed by the box. So let's draw what we have so far. So this is going to be our rectangle, and its length is 10 centimeters. Our width is 8 centimeters. And now we're going to cut out these squares out of each corner that are 2x by 2x. And so once we have all that down, then we know the length of this side is actually going to be, now if we kind of look at the box, if I can draw this here, and then it's going to go like this. And then, all right, so it's not exactly how the height would be, but it's easier to draw that way anyway. All right, so this is going to be folded. So this is going to be 10 minus, and we have 2x here and 2x here, so that's going to be 4x. And this one, the width, is going to be 8x. or 8 minus 4x rather. So it's going to be 8 and then minus 2x here, minus 2x here. So that's 8 minus 4x. And then our height, when we fold that up, it's going to be a height of 2x. So that's going to be what our box looks like. And again, it's not to scale, but it's to how I can draw anyway. And so that's going to be our box. Now, how do we find volume? Well, volume is just equal to length times width times height. And so since we're in terms of x here, we'll say v of x equals our length. Well, our length was 10 minus 4x. Our width was 8 minus 4x. And our height was 2x. Okay. So now what we want to do is we want to write the polynomial functions. So in one form it's like this, but they actually want it all multiplied out. And so we get a multiply out here. So we'll multiply here, that's going to be 80, and then that's going to be minus 40x, then minus 32x plus 16x squared, and that's still times 2x. So I'm going to simplify. I'm going to put the 2x out front, and I'm going to rewrite it in descending order. So that's going to be 16x squared. And then 40 minus 32, that's going to be minus 72x. And then plus 80. So now I multiply here. That's going to give me 32x to the third. And then minus, and 72 times that's going to be 144x squared. And then 2 times that's going to be plus 160x. And so that is my v of x, okay? So that's the volume of the box expressed in terms of x. And so that would be what they want for that first part. So that's good to go there, okay? All right, so the next thing is they want us to find the size of the squares that should be cut out to maximize the volume enclosed by the box. And so now we get to use technology, because what we're going to do is we're going to plot this equation, and we're going to use features of our calculator to find the maximum. So going back to our calculator, and I'm not sure where this was going to graph, but we'll type in our new graph here. And so we had 32x to the third, and then we had minus 144x to the second plus 160x. And so that's going to be our equation, and we graph that. And of course, it's nowhere close to what we need. So our window, let's say we go, looks like the minimum is going to be, maybe we'll put 40 here. And then let's see what that looks like. That's still not enough. Let's do 120. There we go. All right, so that's what the equation looks like. And again, if we would have plotted it as factored form, we could have got that as well. You know, we didn't know it went through that as a straight line, here is a straight line, and up there is a straight line, and then we could have got a general curve. So now what we want to do is we want to find the maximum. And so this is the only place where it's going to be. This is going to be our local max. And so what we're going to use is we're going to use this second trace function. And we want the 4. We want the maximum. Okay. Now our left bound, we can kind of maybe choose that as our left bound. And then let's go on to the other side of the peak, choose that as our right. And then we'll maybe say that, okay, is that our guess? And so this tells us now what the maximum is right there, okay? So now what I'm gonna have to do is, let me see, do I have this written down? I do. So now what we need to do is go back to our other page. And so it said that for our function, x was equal to roughly 0.74, and there's some more, but I'm going to round it to 2 decimal places. And that was then at a y of 52.51, again rounded. Okay, so that was what that peak xy value was. Okay. And so what we have now is we have our x, and so that's what this, x is here. this is what this x is here, and this is what this x is. That's where the x is going to be max. And our max value then is at that point. So what we need to do is we can say that the max volume of the box is 52.51, and here we have centimeters, so it's going to be centimeters cubed because it's a volume, so it's a cubic. And then what we need to do now is what they said is what size of squares should be cut out. And so what size are the squares? Well, basically it's going to be 2x by 2x. And so we take 2 times this, so 0.74 times 2, so it's 8, that's 14, move it over. So the square is 1.48 by 1.48. And that's, again, centimeters and centimeters. And so that's the size of the square that we're cutting out in each of these corners. So when we fold it up, that's going to give us the maximum volume of the box. So that's our maximum volume. That's the size of the squares. And that's our polynomial function in terms of x. And so using our calculator, we got this whole part on the right. The stuff on the left we had to calculate all by hand, and then we were able to use technology to give us the final values over here. Good. Any questions on that? Again, the cool features on the calculator, we were able to find max and min, so sometimes you might have to find the minimum value, and that was going to be number 3. We used the maximum value, which was the second trace, number 4. And then we just had a highlight around, you know, where that was at. So in the case of this, you know, we picked a point here and we picked a point here, and we said find the maximum in that range, which then it found is that where x was at 0.74 and the height was at 52.51. All right, so what I'll do is I'll do one more example here. And then after that, I'll do a bunch of other examples on a separate video later. All right, so this one we have a cylinder, and it has a radius of x plus 2 centimeters and a height that's 3 centimeters greater than the radius. And we're supposed to express the volume of the cylinder as a polynomial function. Now notice this one doesn't ask us for finding the maximum or anything like that, and that's because it won't work really as far as how the function works. And so all we can do is give them the volume as a polynomial function. So what we have is a cylinder. And so we have a radius, r equals x plus 2, and that's in centimeters. We have a height, which is this, and that's going to be 3 centimeters greater than that. So that's going to be x plus 5 centimeters. And now we need to know what is the volume of a cylinder. Well, remember, volume is just going to be, well, first the volume of the circle, that's going to be pi r squared times the height, which is h. And so now we just plug in the values we know, which is kind of right here, everything we know, and we say it's in terms of x. So v of x equals, and we have pi times r, which was x plus 2 squared, times h, which is x plus 5. And now all we have to do is we have to multiply that out. All right. So that's going to be pi times, and if we square that, that's x squared plus 4x plus 4, and then that's still times x plus 5. Okay. Now if we FOIL that out, rainbow it, however you want to look at it, we take x squared times x, so that's going to be x cubed, 4x times x, so that's going to be plus 4x squared, and then 4 times x is plus 4x, and we take 5 times everything, so plus 5x squared, plus 20x plus 20. And so now we've taken each one of those times everything there. Now we like terms is what we need to add. So we have those, we have those. So that's equal to pi times x cubed. Then we have plus 9x squared plus 24x, then plus 20. Okay. And so let's see, what else do we have here? That's looks like that's as simplified as we can get. And since pi is, pi, we'll just leave it out front here so we don't have to have a pi times everything. And so when we're plugging it in our calculator, we don't have to do all that. And so that's going to be our v of x. And so that's the polynomial function for the volume of this cylinder, given the r is x plus 2 and the height is 3 centimeters larger. Any questions there?